Okay, today I'll be explaining 9.1 temperature and thermal equilibrium. What is temperature? Temperature is a measure of the kinetic energy of the particles in a substance. Now, when temperature increases, the kinetic energy of molecules increases, which is directly proportional. Now, adding or removing energy usually changes temperature. It is measured in Celsius, which is Tc equals to 5 over 9, Tf minus 32. Then Fahrenheit, which is Tf equals to 9 over 5, Tc plus 32. Then we have the SI unit of temperature is Kelvin. So changing Celsius to Kelvin is adding 273, and from changing Kelvin to Celsius, we subtract 273. Now, what is internal energy? Internal energy is the energy of a substance due to both the random motions of its particles and to the potential energy that results from the distances and alignments between the particles. The sign is U. Now, we have different forms of energy. We have translational, rotational, and vibrational. Now, translational, it moves like that. And then for the rotational, it rotates. And then vibrational, it could stretch or bend. Thermal equilibrium. Thermal equilibrium is the state in which two bodies in physical contact with each other have identical temperatures. Now, here we have cold tea and hot tea. Here there is less movement of particles. Here we have a higher movement of particles. So, here in part one here, the two teas have different temperatures. Now here, when they come in physical contact, so when the two cups come in physical contact, the energy will be transferred. They will reach the same temperature, which is the thermal equilibrium. As we can see here, Fahrenheit, in the ice point, it's 32 degrees Fahrenheit. Steam point is 212 Fahrenheit, and Celsius is 0 Celsius at ice point, and steam point is 100 Celsius. And then Kelvin, in the ice point, it's 273.15 Kelvin, and in steam point, it's 373.15 Kelvin. Now we reach the practices. Let's try some practices. Now here, 37 degrees to Celsius to Kelvin, said we add 273. So 37 plus 273, which is going to be 310 Kelvin. Then we have this one. We add also the same thing here, so we add 50 plus 273 equals 2. Equals to 323 Kelvin. Now we have a different one, changing from Kelvin to Celsius, which is 211 Kelvin to Celsius, so we subtract 273, so the answer would be negative 62 degrees Celsius. Now, another two practices. The lowest outdoor temperature, ever recorded on Earth is negative 128.6 Fahrenheit, recorded at Vostok Station, Antarctica in 1983. What is the temperature on the Celsius and Kelvin scales? First of all, let's know what are the givens. Now, so we have Fahrenheit, and then we also have, so we have the Fahrenheit, that's what we only need. So, negative 128.6 degrees Fahrenheit, 0.6. So, first, we have to change it to, so we could find the Celsius. So, first of all, they said we need the Celsius and the Kelvin. So, let's find the Celsius first. So, we use the formula of Celsius, which is Tc equals to 5 over 9 Tf minus 32. So, 5 over 9 over Tf, which is negative 128.6 minus 32. So, the answer would be negative 89.22 degrees Celsius. Now, to Fahrenheit, if you want to change it to Fahrenheit, we have to add it. So, negative 89.22, we have to add 273. So, the answer would be 184 Kelvin. Now, the other question. Here we have 105 degrees Fahrenheit, and then we have it in, this is in summer, while we have in winter, but before that, the temperatures of one northeastern state range from 105 Fahrenheit in the summer to negative 25 degrees Fahrenheit in the winter. Express this temperature range in degrees Celsius and kelvins. So we have the givens for summer. It is 105 degrees Fahrenheit. And in winter, negative 25 degrees Fahrenheit. So let's find for both of these. So in summer we said it's 105 Fahrenheit. So let's find TC. TC equals to TC. We said that it equals to 5 over 9 TF minus 32. So 5 over 9 TF, which is 105 minus 32. So we find that TC equals to 40.5. So it will be 41 degrees Celsius. Now for Fahrenheit, so we have to do, for Kelvin, we're going to do 300. Before that, we have to add 41 plus 273, which is going to be 313.5. So we just round it and it's going to be 314 Kelvin. Then we go to the winter, we use the same thing, TC, we use the same formula, TC equals to 5 over 9, TF minus 32, 5 over 9, TF, which is negative 25 minus 32, so TC will equal to negative 31.6, so it will be rounded, it will be 32, negative 32 degrees Celsius. Then for the Kelvin, we said that we have to add it, so negative 32 plus 273, so the answer would be 241 Kelvin. Now we're that's all for section 1. Now section 2, defining heat. What is heat? Heat is the energy transferred between objects because of a difference in their temperatures. Now the symbol for heat is the Q, and the unit is joules. Now, when there's no temperature difference between a substance and its surroundings, no net energy is transferred as heat. Now, the symbols for each one of the energies. Now, potential energy is PE, kinetic energy is KE, internal energy is U, heat is Q, and 1 cal, the small cal, equals to 4.186 joules, and the big cal, 1 big cal, equals to K cal, equals to 10 to the power of 3 cal, which is 4.186 times 10 to the power of 3 joules. Now, energy is transferred between substances as heat. Now, as you can see here in the picture, now we have, this is a can. Here, the transfer particles kinetic energy as heat. Now, as you can see here, the temperature of the water is 5 degrees Celsius, and the temperature of the juice is 45 degrees Celsius. So, when they come together, and in physical contact, their temperature will, both of them will have the identical temperature, so they will reach thermal equilibrium. So as you can see here, the T of the water, it will increase to 11 degrees Celsius, and the T of the juice, it will decrease to 11 degrees Celsius. Now, energy transfer is done in 3 ways. First of all, thermal conductions, such as solids like in direct contact, for example, frying an egg. Second, convection, like as in fluids such as gas and liquid. Example, heat in a car. When you enter the car, you feel that it's so hot. That's an example. And particles moving in a hot Nescafe. Third, radiation, which is electromagnetic waves. And first, like an example is placing your hand above a candle which is on fire. So as you can see here, this is equilibrium. There's the water inside the can or the cup, and water outside. So energy is transferred between the two waters. So water will go in and water will go out, and they will have the same temperatures, 11 degrees Celsius here and 11 degrees Celsius here. Now energy, we have mechanical. We said that energy is done in 2 ways, we have mechanical and non-mechanical, as we knew before. And the mechanical, we have kinetic energy and we have potential energy. Kinetic energy is half times mass times velocity squared, and then the potential energy is mass times gravity times height. Now, energy equals to KE, which is kinetic energy, plus PE, which is potential energy, plus U, which is the internal energy. So then we're going to have EF, EF EI initial equals to EF. So it will be EF minus EI. which equals to 0. It will come here, so then it will equal to 0. So so delta E, or the energy, will equal to 0. So the conservation law of energy is delta KE plus delta PE plus delta U, which is the internal energy, will equal to 0. Now, we have some practices. Now, here we have. First of all, let's read the question. Okay. A worker drives a 0.500 kilogram spike into a rail tie with a 2.50 kilogram sledgehammer. The hammer hits the spike with a speed of 65 meters per second. If 1/3 of the hammer's kinetic energy is converted to the internal energy of the hammer and spike, how much does the total internal energy increase? Now, let's first of all take out the givens. Now, first of all, we have the givens, which are, now here we're not going to use this the 0.5 kilogram spike. We need the 2.50 kilogram of the sledgehammer, because we need it just for the sledgehammer, not for the spike. So here they're asking for the internal energy, and they're not, so they gave us, so as you can see, the question, if you want to use a formula, it depends on the question itself. It depends on what did they give you from givens. Now, so here we have, first of all, velocity equals to 65, which is meters per second, so 65 meters per second, and they also gave us the mass, which is 2.5 kilogram, and that's it. And we know that, yeah, that's it. So as you can see here, they didn't give us height, so that means there's no potential energy, but they did give us velocity, so there is kinetic energy. So as you can see here, so we're going to write that delta KE, remember the conservation law of energy, KE plus delta PE plus delta U equals to 0. So this will go to the other side, because we need to find, actually, yeah, so we need to find the internal energy, which is U, and we said that we don't have the potential energy, so we just use the internal energy and the kinetic energy. So it will be delta U equals to KE. So it will be delta U equals to half times mass times velocity squared. So delta U half times mass, the mass, we said that it's 2.5, and times the 65. So the answer will equal to 1.7 times 10 to the power of 3 joules. The unit is joules. Now the second question. Now, a 3.0 times 10 to the power of negative 3 kilogram copper penny drops a distance of 50 meters to the ground. If 65% of the initial potential energy goes into increasing the internal energy of the penny, determine the magnitude of that increase. So as you can see here, what do we have? Here we don't have the kinetic energy because they didn't give us the velocity, but we do have the potential energy because they gave us the height. So now here we're going to use, so let's write the givens. Here we have the mass, 3.0 times 10 to the power of negative 3 kilogram. And we have the height, which is 50 meters. And 65%. So it will be like delta U equals to 65 over 100 PE. It will equal to 0.65 times the mgh, then 0.65 times the mass, which is, we said that is 3.00 times 10 power of negative 3 times the gravity, which said it's 9.8, or you can make it just 10, and the height, which is 50. I'm going to make it more clear. So 0.65 times the mass, which is 3.0 times 10 to the power of negative 3, which times 9.8, and then times the 50. So the answer will be delta U equals to 0.95 joules. That's the answer, 0.95 joules. Okay? Now, moving on to section 3. So we finished section 2. Now, changes in temperature and phase. Now, same change in energy can cause different temperature change. That is due to difference in particles' motion at microscopic level. The change in temperature due to adding or removing a given amount of energy depends on the particular substance. So it just depends on the substance itself. So for example, like we're putting two different types of metals, let's say aluminum, copper. First, it was placed in a hot, with the same energy or the same temperature. Then we put it in a different temperature to cool it down. Let's say it was first, we put it in hot water, then we put it in a cold water. Both of them will have different temperatures. That's because they are both different types of metals, or they're both different substances. Now, specific heat capacity. It is the energy required to change the temperature of 1 kilogram of that substance by 1 degree Celsius. So we have the two formulas, Cp, which is the specific heat capacity, and the unit is joules per kilogram degree Celsius, equals to Q over the mass times the delta T. Delta T is the temperature difference, and the M is the mass, and the Q is the heat. Then you also have the other formula, which is Q equals to Cm delta T. Now, the specific heat capacity is specified in a way given constant pressure and volume. So pressure and volume, don't forget that. Now, as you can see here, everything has specific heat capacity, as in everything has a density. Now, here they are all mentioned, and we know that the water is the most known one, which is 4.186 times 10 to the power of 3. The unit is joules per kilogram degree Celsius, which is the specific heat capacity unit. Now, calorimetry is used to determine specific heat capacity. Now, energy absorbed by water equals to energy released by the substance. So, the heat of the water equals to negative the heat of the metal. The heat of the water is positive, and the heat of the metal is negative. So here it's like positive, and here it's negative. So we have here specific heat of the water times the mass of the water, and then this is the temperature change, equals to negative the specific heat of the metal and the mass of the metal. And then we have also here the difference in the temperature. Now, calorimetry is an experimental procedure used to measure energy transferred from one substance to another as heat. So as you can see here, this is the calorimetry. Calorimeter. So this is the stirrer, this is the thermometer, this is the lid, and here is the water, and here is the metal placed here, or the test substance. Here's the inner container, and here insulated outer container. Now we have some practices we'll try. I solved it already because it will take time, so it's better to solve this and then I'll explain it. What is the final temperature when a 3.0 kilogram gold bar at 99 degrees Celsius dropped into 0.22 kilogram of water at 25 degrees Celsius? Okay, now, so what is the final temperature when a 3.0 kilogram gold bar at 99 degrees Celsius is dropped into 0.22 kilogram of water at 25 degrees Celsius? Now, first of all, the givens. Now, the two known givens, that the specific heat of gold, as you can see here, it's given already, and also the specific heat of water. So, specific heat of gold is 1.29 times 10 to the power of 2, and the specific heat of water is 4.186 times 10 to the power of 3. So, these are like already given. Then now, we go back to the question. Now, we know that the mass of the gold, here they said that it is 3.0 kilogram, and the mass of the water is 0.22 kilogram. Now we also have the temperature of the gold is 99 degrees Celsius, and the temperature of the water is 25 degrees Celsius. What do they want? They want the T final, or the final temperature, the TF. Now, as you can see here, we have known this before. We said that this is the energy absorbed, and this is the energy released. So Cp, which is the specific heat of water, times the mass of the water, and then here we have the difference in temperature. Now here, negative the specific heat of the gold and the mass of the gold, and then we have the difference in temperature. So we will just like move around the formula, and it will be, because we need to find TF, we need to find TF. So TF equals to T of the water, so it will be T of the water times specific heat of the water times the mass of the water plus the T of the gold, or the temperature of the gold, times the specific heat of the gold times the mass of the gold. No negative here. Then down we put the same thing, but without the T's. So it'll be like the specific heat of the water times the mass of the water plus the specific heat of the gold times the mass of the gold. So first of all, we have everything given, so we just substitute everything, and then we'll find out. So here I found everything. So we found this, and here this, and then this, and then we also found here over this thing. So here we found all the numbers. Okay, so now we're just gonna replace each of one of them, because you have everything given. So you just replace with this formula. So you found out, now you divide it, and then you put it as in TF equals to 47 degrees Celsius. So the main thing that you just need to know the givens, and you also need to know the formula, and then you substitute everything. But it's just a long step. It has long steps. So yeah. So TF will equals to 47 degrees Celsius, and that's all. And thank you.